Hi everyone, my name is Lee and I'm going to present our work, which is a joint effort between the University of Wollongong and Hamad bin Khalifa University. We introduce UOW-Vessel, a new benchmark dataset of high-resolution optical satellite images for vessel detection and segmentation. Vessel recognition from remote sensing images has application in many domains, including defense, border control, law enforcement, fishery management, and vessel traffic management. In this area, existing public datasets only provide bounding box ground truth, which has some limitations, such as overlapping bounding box and redundant background information due to the ship large aspect ratio. Therefore, we developed a dataset for vessel detection and segmentation from optical satellite image and offer more accurate polygon annotation of the vessel objects. This dataset is expected to support instant segmentation-based approach, which is a less investigated area in vessel surveillance. So here's the overview of the dataset. We collect the image from 35 naval bases around 14 countries. The dataset consists of 3,500 images and around 35,600 instances. The dataset contains 10 vessel categories, including aircraft carrier, landing, cruiser, destroyer, frigate, patrol, corvette, submarine, other military, and civilian. We annotate this dataset using polygon with 3 levels of complexity, and the image resolution in this dataset range from 8,000 by 4,000 to 8,000 by 6,000 pixels. This figure shows some samples of the annotated vessel objects. Here we present some key statistics about our dataset. First of all, this table shows the distribution of the number of instances per category. The distribution indicates that there is a class imbalance in the dataset, where 68% of the dataset belong to the civilian class. The class imbalance reflects the real-life scenarios, where civilian vessels tend to outnumber other classes, and certain classes like aircraft carrier and cruiser have fewer instances. Overall, 55% of the dataset has one unique class in an image. The largest number of unique classes an image has is 7 classes, which account for only 0.3% of the dataset. On average, each image is annotated with 10.2 instances, and 40% of the dataset has 1 to 3 instances in an image. Furthermore, most of the vessel instances in our dataset have a relatively small size compared to the image size. So around 65% of the instances have a relative area smaller than 5% of the image area. So in this work, we use instant segmentation networks to detect and segment vessel objects in our dataset. We evaluate 3 types of methods, including 2-stage, multi-stage, and single-stage methods. Here are the experimental results for all methods on 3 levels of annotation complexity. In level 0, all ships are labeled as vessels. In level 1, ships are labeled into 2 categories, military and civilian vessels. In level 2, ships are labeled into 10 subcategories. All of the results are reported on the test set of our dataset. So overall, the results shows that the detection and segmentation performance generally decrease as the tasks become more fine-grained. Moreover, we can see that the YOLO method achieves better performance than other methods in terms of both prediction accuracy and inference speed. So here we show some visual results of the YOLO method on our test set. It can be seen that compared to YOLO version 5 and YOLO version 7, YOLO version 8 can generate finer segmentation masks, and it can detect objects in cluttered scenes. However, all methods still wrongly classify the vessel categories, which is likely due to the interclass similarity problem, where vessels in different classes may have similar appearance. In this ablation study, we test the model performance in challenging weather conditions, including sun gleam, cloud haze, and poor illumination. We can see that the model performed quite well in normal and sun-glint condition. However, the performance decreased in other settings, possibly because the visual features of the vessel are obstructed by poor weather and lighting condition. We also conduct an ablation study on the effect of input image size to the model performance. The result shows that the detection and segmentation accuracy generally improves as the image size increases. In this confusion matrix, we can see that the prediction of all categories improve when increasing the image size, especially for lower performing categories such as patrol, corvette, and landing. The improvement is likely due to the model's ability to capture finer details of the vessel object when the size of the vessel object increases, which is crucial in fine-grained vessel recognition tasks. However, the trade-off between prediction accuracy and inference speed should be considered when the model is applied to practical application. While recent methods have shown notable performance, there is still significant potential for improvement, and we expect that the UOW-Vessel dataset will facilitate the development of new algorithms for vessel detection and segmentation. Thank you for your attention.